So for this question, we should be using the I equals AV, right?
Possibly. What are we actually trying to figure out here?
Guess we're ranking the magnitude of velocity and current for the three from greatest to least.
Yeah, because it looks like we've got three different currents to consider here. We've got the current flowing through this main pipe. So let me label those. We've got this incoming current, and then we've got a current in this pipe, and we've got a current in this pipe. So let's call those, let's say I sub 0, I sub A, and I sub B. The I sub 0 is the current flowing in this main pipe, and then branch A looks like it's the wider one, so current A in this wider one. And then current B in the narrower one. And what do we know, before we even run any calculations, what do we know about how these currents are related to each other?
Well, shouldn't IA plus IB equal I naught?
Yeah, we know that from the junction rule, or the continuity principle, that the current flowing in has to equal the current flowing out. So the current flowing into this junction has to equal the current flowing out of this junction. IO, the current flowing in, equals IA plus IB, the total current flowing out. So we know that much at least. And what does that tell us about IO as compared to IA and IB?
It's going to always be greater than either one individually.
Yeah, we know that IO is the greatest. And of course, that's only guaranteed because we know all the currents are positive. If some were positive and some were negative, then that wouldn't be the case. But we're essentially defining current to always be positive here. Negative current just means the current's actually flowing the other direction than what we've shown on the diagram. And we're assuming all the currents are flowing in this direction anyway. So IO is definitely the greatest. As for IA and IB, any thoughts on how the current splits up in terms of which one's going to be getting more or less current?
Can you just look at it intuitively because IA is larger than it will receive more current?
I would expect IA to get more current, yeah, because there's, I mean, usually if there's resistance involved, you'd look at it in terms of which one has less resistance. In this one, though, we're assuming there's negligible resistance. It says assume negligible dissipation through the pipes. So resistance is assumed to not be a factor here at all. So we can't really rely on resistance. Instead, I would think of it as if you just got a bunch of water particles moving forward, and you're basically just putting a wall here and splitting up the flow. There's more space below the wall than there is above the wall. So presumably there's more molecules that are redirected under the wall than above the wall. So based on that, I would assume that current A is larger than current B. So I think we can expect here that current O is greater than current A, which is greater than current B. That would be my conclusion here.
How would so if resistance was at play and A and B are just like in this example, they're different sizes. How would you then determine which
If we
current?
didn't have resistance, then I would assume that whichever branch, since these are in parallel, this split pipe, they're in parallel. And presumably so they start at the same high pressure, and they're presumably going to end at the same low pressure. So in that case, I would expect whichever one has less resistance would get more current. In fact, this isn't really a very realistic situation, assuming that the assumption that there's no resistance is not very realistic. I would assume that in a situation where there actually is resistance, then resistance would be the most important factor. But cross-sectional area plays a role in resistance anyway. So all things being equal, I would expect the wider pipe to have less resistance. Of course, if the pipes are different lengths or made of different materials, that might also make a difference. Any other questions on that so far? And what about velocity? How would we be able to compare the velocities here?
Can we use the Bernoulli's equation and see how both differ in the A pipe and the B pipe?
Um, I'm not sure if the Bernoulli equation is going to be very useful here because the Bernoulli equation is most useful for comparing 2 points in the same fluid system. Do you see any pairs of points we could use to compare here?
No.
I was thinking you could think of it intuitively. So like if IO is larger than IA or IB, and then we know the cross-sectional area is also the largest, then doesn't the velocity have to be the smallest?
We got to be careful about that though, because the idea of the applying the continuity principle there, the idea that A1 V1 equals A2 V2, that really only applies if, well, what did A times V, what does area times speed mean in the first place? What is that equal to?
Current, right?
Right. So this equation relies on the assumption that the currents are the same in the first place. If current 1 equals current 2, then area 1 speed 1 equals area 2 speed 2. But we can only make that conclusion if we know the currents are the same. Are all the currents the same here?
They're not.
So that means we can't really rely on that assumption. One thing I think we can do though, it might help to imagine currents B and A, or pipes B and A as just one strangely shaped pipe. Like if you take a look at the cross sections here, let me try sketching this out. If you look at the cross section of pipes A and B together, their cross section is this figure 8. So we've got pipe B, and then below it, pipe A. Pipe B, pipe A, as cross sections. And we've been thinking of them as 2 separate pipes, but I think it might be useful to instead think of them as just one strangely shaped pipe. If we think of the cross section here, if you imagine removing that wall in the middle, so we just have, if we just think of this as one sort of figure 8 shaped pipe. So if we just treat this as one pipe called pipe AB, what's changing when we go from pipe 0 or pipe O to pipe AB?
I guess the cross-sectional area is different, right?
Yeah. Pipe AB has cross-sectional area. We've got 2 square centimeters from A and 1 square centimeter from B. So the area is 3 square centimeters. Meanwhile, back in pipe O, what was the cross-sectional area?
4, I think.
Yeah. So if you think of pipe O changing to pipe AB, we've shrunk the cross-sectional area. So we're going from a circular cross-sectional area of 4 square centimeters to a figure 8 cross-sectional area of 3 square centimeters. The cross-sectional area has decreased. So what has to happen to the speed?
It increases.
Yeah. So we're going from slow speed to fast speed.
Isn't that using the continuity principle though, or is it kind of different?
But if we treat A and B as just one unified pipe, if we just sort of imagine merging these together, treat this as just one big pipe whose current is IAB. In that case, we do have continuity. We've got this pipe with circular cross-sectional area becoming a pipe with this pinched in figure 8 cross-sectional area. So in that case, we can treat this as current 1 equals current 2 because the incoming current IO is the same as the outgoing current IAB. We're just combining those together and treating them as just one big pipe.
Which is based on the equation that we made that the I naught equals I plus IB.
Exactly. We're just treating IA and IB as merged together into one current. So since overall we're going from a wide pipe to a narrower pipe, even if it's strangely shaped, the fact that we're going from wide to narrow means we are going from slow to fast. The decrease in cross-sectional area overall means an increase in speed. So it looks like pipe O is definitely going to be the slowest in terms of the actual speed of the water, not the current. It has the most current, but it's going to have the slowest speed. And then pipes A and B are going to have a faster speed. As for comparing those two speeds, I think it might help to look at this again in terms of the looking at the wall between A and B as if it's splitting up the flow. We've got this flow of water, all these water molecules moving effectively in unison. And we have so we've got these water molecules moving and we have a wall. The water gets split by the wall. So the wall is splitting the water into two streams, but I wouldn't expect that wall to be changing the speed of the water as it flows past. It just divides it into two pieces. But I would expect pipes A and B to have the same speed as each other, which is a faster speed than pipe O. Any questions on that?
How would we then, or sorry, I guess maybe you just answered this, but dividing, so we've said that the current for AB is larger. I mean, sorry, the velocity for AB is larger than I naught, but then like we have to divide it up between, how do we divide then, like distinguish between B and A for then which
Well,
one
velocity
has?
doesn't get divided up. The faster speed we're talking about for AB, if you go back to this idea of the cross-sectional area or the cross-section thing, we were pretending for the moment that the wall between A and B is gone, that AB are just one pipe together with this sort of figure 8 shape. And that the fact that the shape is sort of pinched in, that means narrower cross-sectional area and therefore a faster speed. But we should probably assume that every molecule in this pipe is traveling at the same speed. If you put that wall back in, if we just add in this wall, that doesn't change the fact that these molecules are traveling at the same speed as these molecules. I would still expect them to all be traveling at the same speed as each other.
Okay, thank you. So as when like circling the answer greatest, middle, least, like we would put middle and great, like how would?
I mean, we definitely know that A and B are going faster than O. So I think the branch A and B would both have the greatest speed. Wait, that's current. A and B would both have the greatest speed. Main pipe would have the slowest speed. And then we found earlier that main pipe has the greatest current, and A has a little bit less current and B has the least current.
Okay, thank you. And then I also see, I guess it says that you can, if two or more quantities are equal, circle both. So
yeah, I think that's what it's getting at.
And I'm sorry, how did you say that B has a lower current than A?
In terms of current, because it's got a narrower cross-sectional area. And I think we might actually be able to get that easier now that we know the velocities. Since A and B have the same velocity as each other, and current equals area times velocity, same velocity, but a wider area means more current. Pipe A has a wider area than pipe B, so I would expect it to have more current.
Yeah, like I guess if we find the velocity first, the problem becomes easier to solve for current.
Yeah. Yeah, otherwise we just have to sort of intuit that when the flow splits up, the wider pipe gets more of it, which I'm not sure we really can conclude on its own if we don't have the idea of resistance.
I think maybe that's also why we solved it the opposite way, but velocity's listed first, probably because they wanted you to think about it like that.
Possibly, yeah. I'm honestly not really sure what they're trying to get at with this problem. It's a very strangely worded problem. But realistically, everything's going to have resistance. Any other questions on that one? All right. I'd also like to get to a problem with capacitors. So let me pull up a new blank page here. And let me just draw a circuit. Let's say we've got a battery. Which is connected to a resistor. And let's say then the current splits into, or the circuit, the wire, I should say, splits into a path with a capacitor. And a path with a resistor.
Casey, I had a quick question. So when circuits are drawn like this, is it any different than when they're drawn and like the wire splits into and then comes back together? Like I don't know if that makes sense, but like, is there any difference as far as the math goes?
You mean as opposed to if we had drawn it like that?
Yeah.
Something like this?
Yeah, and they end up, yeah.
Yeah, that's the exact same thing.
Okay.
If we had had like a capacitor here and a resistor here, yeah, that would be exactly the same.
Okay, thank you.
The shape of the wire does not matter. All that matters is what's connected to what else. So there's often many different ways to draw a circuit in terms of how you're drawing the wires. But in any circuit diagram, focus on what's connected to what else. Like in this case, we've got a battery, which the positive terminal is connected to one end of a resistor. The other end of that resistor connects to both a capacitor and a resistor. The other ends of those capacitors and resistors are connected to each other and also connected to the negative terminal of the battery. So focus on the connections. What's connected to what else? The shape of the wire does not matter one bit. So let's say we have some numbers here. Let's say we know the epsilon for the battery is let's call that 12 volts. And let's say these resistors have resistances, let's say 1 ohm and 5 ohms. And this capacitor has capacitance 2 farads. I should probably label those resistances also. Let's call that R1 or R2. And let's assume the capacitor starts off empty. And what we want to do here is we want to make a graph of graphs of the capacitor or the charge on the capacitor at any time and the current through each resistor at any time. So that's our goal here. We want to make a graph of two graphs really. And I guess we really want three graphs, but two of them we can put on one graph. We're going to want a graph of time versus charge on the capacitor. And let's also make a graph of current through each resistor. As time passes. So this second one is going to have actually two curves on it, current through resistor 1 and current through resistor 2. Any questions on the setup so far? And in terms of current, how many different currents would we expect in this situation?
Is there two, one for each parallel?
There's definitely going to be one for each of those parallel branches, yeah. So we could label, let's say, it's too big. Let's say we label current through the capacitor and also current through resistor 2. And I'm going to label those IC and I2. And because of the capacitor, these currents are going to be changing as time passes. However, those aren't the only currents involved. What other current or what other circuit element is going to have a different current through it?
Oh, when it's a single unified current, it's like the R1 one, and then after they come back together.
Yeah, because we've got this branch here. The battery and resistor 1 are in series with each other. That branch is going to have its own current. So let's call that I1, since it's the current in resistor 1. It's also the current flowing through the battery, so in some cases we might call that I sub 0. But it's also, since it's the current flowing through resistor 1, let's call that I1. And so in the current graph, we'll actually want to graph all three of those, current 1, current 2, and current C. So what sort of shape would you expect these graphs to look like? Do we know any starting values?
Is the capacitor uncharged?
Yeah, we're assuming the charge on the capacitor is 0 at the beginning because we're assuming the capacitor starts off uncharged. So we can at least put a mark on the charge graph. We know that at time 0, we've got 0 charge.
We know the asymptote for the charge 1, 2, right? Because it's 12 times 2. Is that right?
Possibly. The thing is that really only applies if you have just a single loop. In this case, we can't necessarily assume that the capacitor is going to get all the voltage of the battery because there's multiple paths that current could take. But we'll get to this is presumably going to approach an asymptote. Presumably we are going to get an exponential change model here that as time passes, because the capacitor starts off empty, but let's take a look at what's happening at time 0. Because in cases like this, if things are not a steady state right now, but presumably might eventually settle into a steady state, I find it very useful to examine what's going on right now at time 0, and separately examine what's going to be happening after a long time. So let's start with at time 0. If we just start listing out things we know the capacitor is uncharged. So we've marked that on the graph. When time is 0, Q is 0. But if we start writing out, if we start looking at voltages here, in fact, I think it's a good idea to just start labeling voltages in a case like this. We know, for instance, what would we call the voltage right before the battery? What's our usual label for that voltage?
So epsilon?
Well, epsilon is the change in voltage from the battery. So that's the 12 volts. But yeah, we usually call the voltage right before the battery 0 volts. So if we just call this location 0 volts, that's just a label. That just means we're going to be measuring everything from this point. So all the other voltages are going to be measured relative to that. We're just calling this location 0 volts. Then what else has to be 0 volts? Where else can we label 0 volts?
After the capacitor and then after R2.
Yeah, here and here. Those are all 0 volts because the property of being 0 volts is this entire region. If you've got points that are connected by just wire, they're going to be at the same voltage. So all these locations, since they're connected by just wire, those are all going to be at the same voltage, the same 0 volts. So it's not just that this corner is 0 volts, it's that this entire section of wire is a 0 volt region. Then you go through the battery and what happens to the voltage?
And it jumps to 12, right?
Right, because the battery adds 12 volts. We started at 0, we add 12, we get 12. So this corner here is a 12 volt region. And of course, we have to stop when we hit the resistor because the voltage can change when it goes through a resistor or when we cross a resistor. The two ends of the resistor could be at different voltages. But this is a 12 volt region. Then we cross over the resistor and we could be at a different voltage. And we don't really know what the voltage is over here yet because we don't know the current. If we knew the current and the resistance, we could multiply those to find the voltage drop. But one other thing we can use is the capacitor itself. What's the usual formula for delta voltage of a capacitor?
Q over C.
Yeah, delta V capacitor is Q over C. And I would usually put a negative there because it's a drop in voltage. Or really because of the directionality involved. The real reason for that negative sign there is that the voltage from the capacitor is an attempt to, the capacitor attempting to push charge out of itself. You try and push charge into a capacitor, the capacitor is going to push back. You leave a capacitor to its own devices, it's going to push current out of itself. So this negative sign represents that the delta voltage for the capacitor is pushing in a direction trying to decrease its own charge, or at least trying to prevent it from increasing. However, what's the charge on the capacitor right now?
0.
Yeah, capacitor is empty. So delta V capacitor is also 0. Anytime you got an empty capacitor, that capacitor has no delta voltage, which means what's the voltage on the top side of the capacitor?
0.
Yeah, that's also 0. We were assuming that we were calling the voltage on the bottom side of the capacitor 0 volts. But if the capacitor has no charge, then it has no difference in voltage. So the voltage above is also going to be 0 volts. This is the worst drawing interface I've ever seen. But yeah, we can extend that 0 volt region through the capacitor up to here, because an empty capacitor provides no difference in voltage. So the other side of the capacitor is also at 0 volts. In other words, an empty capacitor acts like just wire. If you just got an empty capacitor, you can treat that empty capacitor as just wire for that instant. And of course, as soon as the capacitor starts to fill up with charge, that is no longer true. But an empty capacitor at that instant acts like wire. And speaking of wire, we can extend this 0 volt region further this way and further this way. This entire zone marked in blue is a 0 volt region. That's all at 0 volts. Any questions on that so far?
I mean, in the beginning, there's no current flowing through that region either, right? Because it's just getting shorted, like that branch where that R2
which region in particular?
The branch where the R2 resistor is?
Yeah, because this R2 resistor, if you take a look at the voltage drop for a resistor, the delta voltage for a resistor is the usual Ohm's law, negative IR. If this resistor has no delta voltage, because the voltage before and after are both 0 volts, same voltage before and after means no difference in voltage, and no difference in voltage means no current. So this is another thing we can conclude. R2 gets no delta voltage, so current 2 is 0. We know that at this instant in time, current 2 is 0.
Wait, so how did we extend it to R2? Like, how do we know that the voltage just doesn't go through the capacitor, but then like it gets stopped at R2?
Voltage isn't really talking about motion. Voltage is more like talking about how much pressure there is at that location. And if you want to compare voltages at two locations, we're essentially setting up almost a Bernoulli equation, but for electrical push instead of fluid pressure. If you compare the points right before and right after the capacitor, so essentially what we're comparing here is this point and this point. If you compare those two locations, the difference in voltage between those two locations has to be delta V capacitor, or negative Q over C. But since the capacitor is uncharged, that means the difference in voltage is 0, since the charge is 0. So those 2 points have to be at the same voltage as long as the capacitor is empty. Which means if we're calling the voltage on one side 0 volts, the voltage on the other side of the capacitor is also 0 volts. So this entire region is a 0 volt region also.
Because they're only connected by wire?
Yes.
Is that, okay.
And of course also connected by the capacitor, but the capacitor is empty, so there's no delta V. And an empty capacitor can basically be treated as almost acting like wire. We could just treat this region of the circuit as if it was just connected by wire. And of course, it's not really connected by wire. There is no way for current to cross that gap. But since an empty capacitor offers no pushback, it temporarily acts like wire for purposes of voltage. There's no difference in voltage from one side to the other. And just as if these had been connected by wire, we would say R2 is shorted out. The empty capacitor in this branch acts like a short circuit, shorting out resistor 2. And we'd say resistor 2 is shorted out because there's no difference in voltage, and therefore no current. But how much current is resistor 1 getting? Or I should say, to start with, how much voltage drop is it getting?
Negative 12?
Yeah. R1 is getting the full negative 12 volts because it's a connection between a 12 volt region and what we now know is a 0 volt region. Meanwhile, resistor 1 is getting the full 12 volts. So its current is, how would you calculate the current there?
You can use Ohm's law, right? Because we have R and we have V.
Yeah, we know delta V, we know R. So we can use delta V resistor equals negative IR. And therefore current is going to be delta V over R, well, with the negative. Delta V is negative 12. The negatives cancel out. Resistance is 1, so just 12 over 1 would be 12 amps. So current 1 is going to be 12 amps. So we can actually start graphing this. We know that that current 1 at the beginning, current 1 is 12 amps, and current 2 is 0 amps. So we can mark those on the graph. I'll put a 12 up here. And so we're going to have 3 different graphs here. We're going to have a graph for current 1, a graph for current 2, and also we'll want current C. Can you figure out what current C is right now? How should we expect current 1, current 2, and current C to be related to each other? It might help to take a look at this junction here. What's the current flowing into that junction and the current flowing out of that junction?
So I1 is equal to IC plus I2.
Yeah, we know we've got I1.
Yeah.
Yeah, and I2 plus IC flowing out. So we can make use of that fact. Yeah, from the junction rule, we know that I1 equals I2 plus IC. And we found that I1 is 12 and I2 is 0, so IC has to be 12 at this time. So we could mark both of those on the graph. Current 1 and current C are both 12. And current 2 is 0. So we know we've got one current that's 12, or 2 currents that are 12. Let me just mark these in different colors. Let's say we've got one of the currents is at 12. One of the currents is at also 12. And one of the currents is at 0.
How do we know that it doesn't, like, the current doesn't split between the two, or how do we know that IC is 12?
We would expect current to split, but that just tells us that current 1 equals current 2 plus current C from the junction rule. But at this instant, we know current 2 happens to be 0 because there's no voltage drop. So that means instead of current 1 splitting some to I2 and some to IC, instead all 12 amps goes through the branch with the capacitor. None of the current goes through the branch with resistor 2 because there's no voltage drop on that resistor.
But I thought we were saying because the capacitor works like a wire, so it doesn't, even though there's 0, the whole region is 0 volts. The capacitor functions like a wire, so it can go through, but at R2, because there's resistance, it won't move.
Yeah, the empty capacitor offers no pushback at all to the current flow.
And just a question, will the delta V cap equal the delta V R2 because they're in parallel?
Yes, the fact that these are in parallel, that is going to be a useful fact throughout the whole process. No matter what happens here, since the capacitor and R2 are in parallel, we know they have to have the same voltage. Delta V capacitor equals delta V resistor 2 always, because they're in parallel. In this circuit, that is. And for other circuits, of course, that's not going to be true necessarily, depending on how the circuit is set up. But in this circuit, as time passes, things are going to change. But no matter what, the capacitor and resistor 2 have to have the same voltage as each other because they're in parallel.
Is that true for all parallel circuits?
Yeah, in general, anytime you've got 2 branches in parallel, the 2 parallel branches both start at the same high voltage and they both end at the same low voltage. So any branches in parallel with each other have to have the same overall delta V. And of course, that's true even if there's more than 2 branches. If you've got like 10 branches that all start at the same point and all end at the same point, each one of those 10 branches has the same full delta V. However, as time passes here, I mean, we do have current flowing. The fact that current is flowing means things are going to change. Specifically, current flowing across the capacitor means the capacitor is going to start to fill up. You're going to start to accumulate charge, positive charge on the end of the capacitor most closely connected to the positive terminal, and negative charge on the branch most closely connected to the negative terminal of the battery. So we're going to get charge accumulating on the capacitor. And charge on the capacitor means the capacitor now has a delta voltage. So we can no longer rely on our previous assumption that the top region was 0 volts. We're going to have to rethink that. We can still say the bottom region is 0 volts because that's what we were defining to be 0 in the first place. But the fact that there is a charge on the capacitor means the capacitor now has a delta voltage, which also means we can no longer rely on the currents we calculated. But what we can do is we can say that as time passes, the capacitor gets more charge, meaning capacitor's charge is going to increase. And the currents are going to change as well. In fact, let's take a look at what happens after a long time. Because like I said earlier, it's useful in cases like this to look at what's going on at the beginning and what's going on after a long time. So we can say after a long time, we have, what would you expect after a long time to happen to the currents? Do we know what any of the currents might be after a very long time?
Should be 0, right? Eventually, because
which one specifically? Because we've got possibly 3 different currents.
Oh, sorry, because they're in parallel. Oh, go ahead.
Sorry. I would say the current across the capacitor is going to be 0 after a long time.
Mm-hmm.
So that means all the current would go through. It's kind of like the opposite, where in the beginning all the current went through the capacitor, but at t equal infinity, all the current's going through R2.
Yeah, because after a long enough time, we've got lots of charge accumulating on the capacitor. And the more charge there is accumulated on the capacitor, the more pushback there is. And so I would expect the current through the capacitor to get slower and slower as the growing charge pushes back more and more. Eventually you get to a point where there's no more charge flowing through the capacitor because it's as full as it's going to get. Because if there is current flowing, then it's not full yet. It's still in the process of filling up. If the capacitor eventually approaches some maximum charge, that means the current flowing through it is going to eventually be 0. So we should expect after a long time, capacitor is full, Q equals some Q max, and the current through the capacitor is 0. It has reached a steady state. There's no more change. And if the current through the capacitor is 0, a full capacitor, we can basically just treat as, since no current is flowing through it, we can treat it as if it's not even there. And now what do we know about current 1 and current 2?
They're equal?
Yeah. Current 1 equals current 2. We can even get that from the junction rule. If you go back to the junction rule, plug in 0 for current C, you just get current 1 equals current 2. And if current 1 and current 2 are the same, now how would we describe how R1 and R2 are connected to each other?
They're in series.
Exactly. If they're in current, if they're forced to have the same current, they may as well be in series. You can also see that if we just ignore this middle section of wire, because no current is passing through the capacitor, so we can ignore it. R1 and R2 are just right after each other in one single path. Since they act like they're in series, how would we combine their resistances?
By adding them, so REQ would be 6.
Exactly. This acts like just a single 6 ohm resistor. And if we now treat this as just one single loop with a 12-volt battery and a 6 ohm resistor, what would the current be?
2.
Yeah, we just take the usual Ohm's law. Current equals voltage over resistance. 12 volts over 6 ohms would be 2 amps. So current 1 and current 2 both equal 6 amps. So that's what's going on after a long time. And we
Sorry,
can.
I think you meant 2
Oh,
amps.
sorry, yeah, thank you. 2 amps. I saw the 6 ohms above it and just repeated that. But yeah, current 1 and current 2 both have to be 2 amps, which means we now have an asymptote. We know that after a long time, current 1 and current 2 are going to approach 2 amps. So we're going to have an asymptote at 2. So I'm just going to draw at 2 amps an asymptote. And we know that both, if we take a look at all these currents, we know that current 1 started at 12 amps and is approaching 2 amps. So we can draw this out on the graph. Current 1 starts at 12 and asymptotically approaches 2. Meanwhile, current 2, what did current 2 start as?
0.
Right. And it's going to approach 2 amps. So current 2 starts at 0 and exponentially approaches. That doesn't look right. Exponentially approaches 2 amps. And I haven't really drawn that to scale. That should probably be a more gradual approach. Or alternatively, we could just make the 12 amps one a faster approach. But they should be approaching at the same rate. They're both going to have the same time constant as each other, same half-life as each other. Meanwhile, what about the current through the capacitor? That started at the full 12 amps of current. What's it going to be approaching?
0.
Yeah, capacitor's current starts at 12 and exponentially decays down towards 0. So this is what the graphs would look like. We've got current through the capacitor starting at 12 and decaying towards 0. Current through resistor 1 starting at 12 and decaying towards 2. Current through resistor 2 starting at 0 and also decaying towards 2 amps. Meanwhile, we could also find out the maximum charge on the capacitor. In a single loop, we would often expect the capacitor to get the full voltage of the battery. But in this case, instead, we know the capacitor has the same voltage as what else?
R2.
Yeah, we know the capacitor has the same voltage as R2 because they're in parallel. And we can now find resistance 2's voltage because we know its current is 2 amps now. Current and resistance can be multiplied to get voltage. So we can now say the final delta V of resistor 2 is 2 amps times 5 ohms, that's 10 volts. So we know that there's a 10 volt voltage drop on R2, and therefore also a 10 volt voltage drop on the capacitor. And for charge, we can just multiply voltage times capacitance. 10 volts times 2 farads is 20 coulombs. So we know the final charge this approaches is going to be 20 coulombs as Q max. We could even fill that in here. We can say Q max equals 20 coulombs. And the graph for that is just going to be exponential decay approaching 20 coulombs as an asymptote.
Sorry, how did you get 20 coulombs?
20 coulombs is from the fact that delta V capacitor equals negative Q over C. And we know that it's, and then if you solve for Q, you just get negative delta V times C. We know delta V is going to be negative 10 volts because it's the same voltage as the resistor. And we multiply the capacitance, 2 farads, and we get 20 coulombs. In fact, using this highlight notation that we've been using, we could even label this region now, we know resistor 1 is getting 2 amps of current and 1 ohm of resistance. So it's going to have a voltage drop of minus 2 volts. 12 volts minus 2 volts is going to be 10 volts. So this is a 10 volt region. Both the capacitor and resistor 2 have a voltage drop of 10 volts because they're going from a 10 volt region to a 0 volt region. And for the capacitor, you can just multiply the voltage difference by the capacitance to get the charge. So the final charge is going to be 20 coulombs as an asymptote. And then we can just draw in an exponential growth or exponential decay curve, I should say, because it is approaching an asymptote. And in this case, since this is all just the same circuit, all of these exponential decay curves are going to have the same half-life as each other. So it's going to take the same amount of time for each one of these to approach halfway towards the asymptote. Any other questions on that?
What did you say? You were saying how this relationship is unique so that you can use R2 for I don't remember exactly what you said, but you were saying when we found that the delta V capacitor, or how we could find Q max, you're saying there was something unique about
Yeah,
the circuit?
specifically that that the voltages are the same. The fact that the capacitor and the resistor are in parallel with each other tells us that they have to have the same voltage drop, because they both start at the same high voltage and they both end at the same low voltage.
Okay, thank you. But you're saying with the series circuit or something, that would not be the case.
Right. It's the fact that this capacitor and this resistor are parallel branches that tells us they have to have the same voltage as each other. And this is often a useful way of figuring out what the voltage on a capacitor is. Maybe you don't know the voltage on the capacitor, but it's in parallel with something else whose voltage you can find. So find the voltage of that parallel branch, and then you can assume that this branch, since it's in parallel, has the same voltage, and use that voltage to find more information. Any other questions on that? All right, then I will see you next time.